About 9 months ago, on a particularly drizzly day, I thought, wouldn't it be fun to 3D print in place my own C-scooter? To make things interesting, I gave the product a couple of interesting design constraints that you won't have seen anywhere else. In this video, I'll show the results of 500 hours of design, build and testing. Stick around to see if it'll actually work right here in the water. Oh, that's cold. The two design constraints are, firstly, that the C-scooter's hull must be printed in place in a single 3D print, so as to encapsulate the C-scooter systems in a single part. I mean, you can incorporate small, simple widgets like magnets and nuts in a 3D print relatively easily. For this to work, it must include motors and batteries as well as a whole load of electronics and wiring. I'm not sure this has ever been done before. Secondly, the hull must be hermetically sealed, with no holes or seals for a drive shaft or electrical connectors to connect the C-scooter's systems to the outside world. So the first challenge I had to overcome was how to waterproof the 3D print. To test this, I built a pressure rig that I could fill with water and pressurize with compressed air to several atmospheres pressure. I printed a whole load of test sample hulls using different print parameters, trying a range of coatings, and tested these at different water pressures, with some pretty striking results. I tried a lot of different materials, settling on ASA with a flexible epoxy clear coat as the final winner. We managed to get it to work up to 4 atmospheres of pressure. The second challenge was how can I drive the propeller without making any holes in the hull? For that, I'll have to rely on the power of a magnetic gear. Magnetic gears consist of 3 parts: an inner magnetic rotor, an iron-filled concentrator, and an outer magnetic rotor. As you rotate the inner rotor, the magnetic flux is focused through the concentrator layer and turns the outer rotor in the opposite direction. I've incorporated the iron-filled concentrator layer into its hull. And here is the inner rotor that incorporates a special 2-pole diametrically magnetized magnet. Here's the outer rotor with 8 long bar magnets encased in a ring of iron to focus the magnetic flux inwards. The motor then gets mounted inside the hull and connects to a shaft of the inner rotor. To celebrate hopefully reaching the 1,000 subscriber milestone with your help, I'll be giving away some of these miniature magnetic gears, surprisingly strong, that I designed. All you have to do to be in with a chance to get your hands on one of these is pop a comment below that starts with the number of times the printer pauses to put more parts in the build during the printing of the C-scooter hull. I'll also pop a comment below with details of the giveaway. The next challenge was how do we control the C-scooter without making any holes in the hull for cables or wires? For that, I had to rely on a lot of sensors and magnets to create a wireless throttle and a wireless master on-off switch for the C-scooter. After testing a few approaches to control the speed of the motor, I ended up using 2 Hall magnetic sensors to create a wireless throttle and auxiliary switch that senses the proximity of a magnet that is outside the hull. The throttle assembly was also tricky to design, as I wanted it to be bistable, so that the throttle was both continuous but could be set at cruise speed as well. The silver cylinder is the magnet that Hall sensor is sensing. I then managed to incorporate this switch mechanism into the C-scooter's handles while it was printing. Pretty neat. So I've achieved a lot, but I've still got a little way to go. So next challenge, how do I power the C-scooter and charge it wirelessly? Well, for that, I'm going to use a custom wireless charging circuit and a lithium-ion battery that I custom built. I'm using 26650 lithium-ion phosphate cells to build the battery, which have a nominal voltage of 3.25 volts each. So to generate enough voltage, I decided to use 8 of these in series to create a 26-volt battery and combine this with a compact 8S battery management system. The main advantages to building a custom battery is that you can design it to fit snugly inside the C-scooter's hull in a 2x4 cell arrangement that will wrap neatly around the drive motor like so. For the wireless charging system, I use an off-the-shelf inductive power transfer circuit. The transmit coil is on the right and the receive coil is on the left, which outputs at 12 volt DC. To get the output voltage of 29 volts that the battery needs to charge, I combine this with a boost converter. I did quite a bit of testing to characterize the power delivery behavior of the wireless charging circuit and decided to use 2 of them in parallel to improve the charging speed and provide some redundancy. In the end, I was able to charge the battery pack at about 1 amp. Right, so we've got all the electronics now. Next challenge is how do I get everything inside the C-scooter? That's going to take some serious CAD and tessellation, I think. Let's see how we get on. When designing the initial test rig, I just stuck a box on the side of the C-scooter to house all the electronics. Each block here represents the space that each subsystem occupies. Even this was fairly tightly packed, and it didn't include either the battery pack, wireless charging subsystem, or motor. Let's see if it's even remotely possible to lay out all the subsystems in the space available inside the C-Scooter's hull. Okay, great! Let's design some standoffs for the subsystems that use the battery pack as scaffolding. Ta-da! Here is the finished C-Scooter's drive system in action. The first step is to add a magnet to activate the master read switch, and then use another magnet to change the distance to the hall sensor to modulate the throttle and motor speed on this side. It was really important to include some signal averaging to get the smooth throttle response that you can see here. One more challenge, but it's a big one. Can I 3D print the C-Scooter in a single piece, in one print? It's going to be difficult. Let's give it a go. Okay, so the plan is to pause the print of the hull at different points so that it can be augmented with all the bits that turn this from a buoyancy aid into a C-Scooter. Let's start with adding the iron bar to the build concentrator layer that is integrated into the C-Scooter hull, followed by a spot of glue to secure them in place. Okay, so far so good. The magnetic gear is done. Let's move on to printing the main chamber of the hull. But that was relatively simple. Next up, what might be the biggest and most complex widget ever incorporated during a 3D print, the drive system. What could go wrong? Here we go. So if this worked, the drive system just needs to be lowered into the hull. Once it makes contact with the bottom, it can be screwed into position and secured in place using the orange tabs that can dock it into the wall of the hull. This also ensures that the drive system is correctly orientated in the hull. So it looks like the print is about to fail, but I managed to save it by realizing that the weight of the super widget has lowered the build plate slightly and manually adjusted the Z offset by about 0.3mm. My suspicion is this came from the elasticity in the Z-axis belt. Next up, the wireless charging assembly. This first needs to be connected to the battery, then lined up with the tabs and tacked in place with another spot of glue. And we're off again. This time, only a small additional Z offset is required to keep the print running smoothly. And it's done. Let's see if we can get this to work when it's still attached to the build plate. Pretty cool, right? Still attached to the build plate. Give it a go. Can you hear that? Wow, still attached to the build plate and it's running. Oh yeah. Sounds good, doesn't it? Let's put the outer magnetic ring on. I'll retainer cap into these holes here. We go, look, we've got a fully built C-Scooter. Okay, you can see the temperature's gone up inside the C-Scooter, so it's logging the data, and you can see on the display, these are all the messages. The last thing to do is to coat the hull in epoxy. Wow, that took a little longer than I was expecting, but I think we've got there in the end with hopefully a fully functioning prototype. Let's take it for a test spin. How about here for a first test drive? Not bad, right? Okay, can we get it out of the bag, please? It's a new one, right?
No, I think it's in yours, right?
What? No. Time for some teleportation. All right, we're going to give this a go. It's the maiden voyage of the sea scooter. Let's see if it'll sink or swim and see how fast it's going to go. Well, hey! Okay. Right. Let's give this a go. This is going to be cold. Very cold. Oh my god, this is cold. Oh god, this is cold. I think we need a bit more power. Bigger mag now, bigger mag. Okay, put it right.